So for this problem, we are trying to find out what is the stress cubes or the stress element at A, B, and A prime point on the same AA cut. So the first step for the combined loading is try to draw a good FBD so that you will know how many internal forces you are going to have and what kind of equations you are trying to use. So again, we are going to choose the free end side as our FBD because if your fixed end calculation was wrong, every internal force calculation will be wrong. So we are going to pick the top as our FBD. So for this problem, the first step is try to draw the FBD and then include all the external forces. And this is the FBD we had. The next step is try to mark the coordinate system on your FBD. So try your best to find the force first because that's easier. So we can see we are going to have the force in the positive x direction to balance the 1500. And this force is going to be a shear force because this force is parallel to your cutting plane. And then we do the 1000. And this force is also parallel to your cutting plane, so that's why it's going to be shear force too. Okay, so we done the force. The next thing you are going to do is try to find the moment and identify is this moment going to be the bending moment or the torque. So which means what you need to do is try to use one force go through every dimensions so that you're not going to missing any moment. So we know the dimensions are. Okay, so I am going to start with 1000 Newton. So now let's take a look. 1000 Newton is parallel to the 0.4 meters, so there's no moment will be created. So which means we can use 1000 Newton go to cross the 0.2 meter. So when you curl your hand, you find out this moment is in the negative x direction. However, our internal force needs to be opposite direction to balance the external. So that's why we are going to draw the moment in the x direction, in the positive direction of x. And this moment is parallel to the cutting plane also. So this is going to be a bending moment. Okay, so we use one force go through two dimensions, which means we can move on to the next force. The next force we are going to use is 1500 Newton. So if we curl our hand for 1500 Newton, you can see our thumb is in the positive z direction. So we are going to create moment in the z direction. Again, internal force needs to flip your thumb. So this moment you can see is actually perpendicular to your cutting plane. So this is actually a torque, not bending moment. Okay, so we still had one more to go, 1500 times 0.2. So when you curl your hand, you can see your moment is in the negative y direction. So which means our moment is actually in the positive y direction. And this is going to be a bending moment because it's parallel to your neutral axis, parallel to the cutting plane. Okay, so we finish the FBD. The next thing we are going to do is based on each force, trying to calculate the stresses. So let's try to use one force each time. And it will be better actually follow the NVTM order, because that's going to from the axial load to shear force to torque and then bending moment from the easiest to the hardest. Okay, so for this problem, let's try to start with the shear force 1500. Because it is a shear force, which means we know we are going to use shear stress calculation. Tau equals to VQ over IT. So now the next thing you are trying to do is, based on your FBD, you can see the point A prime, and B. So which means what we are going to do, it will be better to draw the whole cross-sectional area and mark all the points. And then try to mark all the coordinate system. The next thing you are going to do is try to mark the force. So based on the FBD, we know this force is actually going into the positive x direction. Why we need to draw the force? Because it will help us identify the neutral axis. Always remember the neutral axis for the transverse shear will be perpendicular to the force. So which means this is your neutral axis. And you can see A and A prime point is actually respect to the neutral axis is either on the top or the bottom, which means the Q will be 0. So which means if we were trying to plot the stress cube at A and A prime point, for shear force Fx equals to 1500 Newton, we can directly write. However, for the stress at B point, will that be 0? The answer is no. Actually, we are going to have the maximum value at B because it's on the neutral axis. So which means what we are going to do is calculate tau B. So shear force will be 15. I like to go through the easy one, which is IT, and finally calculate Q. So what is the cutting width? Are we going to use 20 or we are going to use different value? The answer is going to be diameter for the cutting width, so which means we are going to use 40. So now let's calculate Q. So Q equals to the area times y bar. So for the semicircle, the area will be, and then the centroid for the semicircle is going to be 4r over 3 pi. So which means we are going to find out the stress at B. Okay, so how we are going to plot this stress on the stress cube? First of all, based on our FBD, we know the cutting plane will be the bottom face, and this is why I try to shade it in my column here. And then, which means we are going to know the stress direction on the bottom face first. So now let's take a look. How could we identify the shear stress direction? So remember, for the transverse shear, the shear on the whole cross-sectional area will be in the same direction of the shear force. So which means we are going to have the shear stress going into, at B, going into the x direction, positive x direction. So this is why on the stress cube, we are going to try to draw the shear stress in the positive x direction. And then after this, you can just use head by head, tail by tail to finish all the 4 shear stresses. Okay, we done one first, which means we will be able to move to the next one. So we are going to